Hello gamers and welcome to another TechnoBabble video. Video game development is a complicated business and can be shrouded in mystery at times, but it can also be a friendly community that can share the knowledge and allow some of these to become a little less fuzzy. And courtesy of GDC 2015, this is the case here. Like my last article on DX12, one that I will be updating soon with a more hands-on set of benchmarks and information, so stay tuned for that looked at the Xbox One and PC development cycle. Here we are looking at the Sony camp and specifically the PS4. Naughty Dog was present via lead programmer Christian Gerling, who was in charge of the single-threaded PS3 engine moving over to the PS4. As you may imagine, migrating such a huge code-base engine from something as unique as the Cell and having it up and running on an x86-64 CPU was no mean feat, but one he and the team managed more than admirably, with the remastered classic The Last of Us, which you can check out my detailed analysis of at launch here. The talk was full of very interesting and insightful details into both life on the PS3 and the PS4. Common knowledge is the fact that the PS3 engine was a 30Hz C30 FPS designed from its inception on the original Uncharted Drake's Fortune, which Christian worked on as one of his first projects. You can see this running behind now. Being the first game on the new engine for the PS3, it suffered from having lots of tearing and not running any VSync, as you can see from my analysis above. This was the same engine that delivered all of its sequels along with the swan song The Last of Us on the PS3. From my earlier software article I explained the PS3 and Xbox 360 in more detail, which to shorten here is that the machine had a weaker GPU from Nvidia, the RSX chip, and was aided greatly by the much stronger Cell CPU that sported 1 PPU and 7 SPUs. One was locked to the OS and the other 6 ran devoted to game code, with which developers like Naughty Dog and others had to use to make up for a deficit in the GPU and VRAM. The SPUs were used for handling pretty much all of the engine system threads, with very little actual game code running on them, with most game code running on the PPU, which is more like a standard CPU structure. It was a completely serialized engine, with game logic preceding render calls via the command buffer generation stage that mirrors how DX11 and most game engines work. This engine and configuration, in Christian's own words, was complicated and difficult for the game programmers to work. Jobs could not end once started, users had to allocate memory along with freeing it when done. Job sync indexes needed to be flushed when filled, which caused big stalls, as evident here from behind with Uncharted 3, with the long hang as context switch happens. Job list arrays covered many jobs running per frame, so the complication of the engine was big, bad and busy, along with it being serial. The specific aim for the PS4 engine was to improve and simplify the engine for the game developers and programmers, and not to improve performance using the fiber job system. It was a secondary byproduct and bonus that fibers also have large performance gains when used, but it was not all plain sailing and benefits, as he explains. By allowing the entire engine to be jobified means to break it down into smaller, manageable chunks that allow jobs to start, wait and kick other jobs mid-execute rather than wait till the end, which is costly and wasteful. Leave all memory management hidden from the user, so they did not need to manage this on each game code's process. Now fibers are a small packet in essence of the entire entity of the job and what is used to fill the stack thread, stack pointer, register, etc. Meaning that the system OS register function which happens from a system call, SC fiber switch, which yields the task from running. This saves the state of the job, thus allowing it to be seamlessly moved with little to no penalty. Each thread, the task that starts each job or fiber, is locked to a given CPU core and does not move. All jobs are executed without exception in these fibers, so that control is manageable with sync points where data race conditions may occur. This is where a variable is being read from and written to by separate entities. This is managed through atomic counters, which handle how and when a variable or dataset is safe to release from a temporary lock. The new engine supports a total of 160 fibers, jobs, in concurrent flow and incomplete, with 128 small stacks of 64 kib and 32 larger stacks of 512 kib that may be used by middleware solutions. These jobs have a low, medium and high priority flag when pushed into the queue that will allow a higher priority job to jump the queue and become the next job to be picked up by a thread, as demonstrated by the image here showing the flowing of each job pulled in, and also can add more jobs itself, which may be as a result of the current job it is executing. In addition, if the atomic counter that is used to see if the job that has been pulled can complete or needs to wait on another piece of data that is still in use, it can be pushed into a wait queue. This is then copied into a wait pool, which is the entire fibre content with all addresses and pointers along with a counter, so that it can be put to sleep until the data is free and can be resumed. This could be the next job to run on this core or another. Once this job is complete, it will flag the atomic counter as 0, which means free to go, and the job that was out in the queue can now be pulled back into the thread to be completed. As the entire stack is copied, this could even happen on another core, other than the one that the job started on. With this being seamless and without contention, that does come, and it's an interesting section of the talk. With the locked 6 cores dedicated to game logic by the engine, because when a system OS call happens, you have to basically claim the core, otherwise the system kernel can take control of the core or any of the thread requests that it needs for a job and evicts the current running task until complete. Without the lock, this can cause a ripple effect, as all 6 cores could context switch as they effectively try to offer up their spot so the actual stop job can run elsewhere. This will, as you may have guessed, cause stalls and hangs. By locking or claiming the cores at the start, this means that only one core will be affected by this and minimise the disruption. The interesting part of this is that CPU core allocation will always be dynamic like this due to it not wanting to waste cycles or cores that are idling. The main kernel can always take control when needed. This could explain some of the hangs you can get in games when loading, saving or notifications from the OSV shell, where explicit allocation of cores does not happen. The context switch becomes more of a performance hindrance by a factor of 6. But I stress, I am only working on the info shown here and my own experience and understanding of how it all works as far as operating systems do. Nevertheless, an interesting nugget of information that gives some insight into the PS4's architecture and OS in practice. This new and very clever dissection of the engine allowed it to run up to 1,000 jobs per frame in The Last of Us Remastered. This means every 16.67 milliseconds, so it was busy. What this means is you no longer have a main worker thread that manages the entire show. Instead, the frame call is started and ended by a small little task, and everything else is managed at a granular level as we have gone through, and cores are not idling waiting on other jobs to finish before continuing, which is incredibly useful along with it being efficient. Aside the small section of a standard I/O from disk or socket activity from network and some other small tasks which are all handled with standard system threads and interrupts, but sleep most of the time and only call another job and then sleep again to avoid hogging a thread. Here is the Naughty Dog profiling tool that shows on the left y-axis the 6 cores available to the game, which is your threads. Along the x-axis for each core is the separate jobs and the work they process fills up the stack or has gaps where it is wasted idle time. With the new fibre system, it removes the need and restriction of mutex locking a shared resource between 2 or more threads, a big issue when you go into multi-threading work, but due to the lightweight balance of the system they cannot use mutex or semaphore flags within jobs. But the entire process has much more benefits over any negatives. One area that has restricted fibres being vastly used yet is due to many debugging tools not supporting them or handling them well. But the PS4 SDK debugging toolbox most certainly does support them and treats them as threads, so the use of these will greatly expand both within first party and third party games, with other IDEs likely adding support recently. It still has some issues with TLS, thread local storage error, that can cause a switched fibre to awake with the wrong pointer, which is the location of data, as it resides in another core's local storage. Again, a flag can be set in some compilers to lock this, another demonstration of how detailed, fiddly and easy it can be to miss settings, features or functions within software development. The talk has more information that I will leave out here, but another system function, priority inversion, was also highlighted that allows a lower priority job to leapfrog a higher one, as it is holding data that the higher priority job needs to complete. This important ingredient to the new system solved most of the remaining locks on the jobs and is interspersed with a new spin from the job system Atomics, just in case that frees up the resource before getting heavy-handed. But from all this information and hard work, you would assume that by now the game was up, the engine was converted and running seamlessly at 60 FPS, and you'd be wrong. With the initial conversion done, The Last of Us PS4 was running at less than 10 FPS, 132 milliseconds per frame. But the entire rendering engine had been changed, but none of that had been jobified, like the engine code. Once this was done, over 100% improvement with the frame time dropping down to 55 milliseconds, but this is still terrible at around 15 FPS. The aim from the team was clear. With the profiler split up into red, blue and green, this was a clear marker for the game and graphics programmers. If you are within green, then you are great. you're at 60 FPS. Blue is good for 30, and red is Assassin's Creed Unity territory, or worse. It's a joke. And even at this point, with all the game engine and rendering jobified successfully, with all 6 CPU cores successfully running in parallel and multi-threaded with extra fibre content, the game was still woefully over budget and under target, with even 30 being a way off. And for anyone in doubt about how tight and close to the knuckle a game or any software can come together, need look no further than this. April, 3 months from going gold, it was struggling to run at 30 FPS, and I'm sure at this point panic was setting in. It will come as a little surprise to know that the GPU was not the issue here. In fact, the GPU regularly had issues that caused it to run too fast, so they had to call a stall and wait so that the engine could get back into lockstep. No, the engine was CPU bound, with the critical path each core of the frame taking 25 milliseconds each to complete, meaning the 16 needed to get 60 FPS was at this point not only off the table, but the entire menu. They had to work out a better way and did not want to just give up and ship at 30, which is what many would have done. Be under no illusion, with modern games in modern engines, 60 FPS is not easy and very expensive, and has to be an initial game design decision at the start of a project. So the next step was to look at the gaps, with earlier wasteful locks reduced to as low as possible, along with the breaking down of each task to a low atomic level. There did not seem much left to look at. Here on the graph you can see that the render logic in red and the game logic in green, but notice the big gaps. The CPU was not being maximised at all, which is a problem, but dropping these gaps, the calculation said that the 100 milliseconds over the 6 cores was within target. 100 divided by 6 equals 16.6 milliseconds, which is the magic number. So the goal was still possible, but how do you do this? Again, at this point they are 2 months to ship and still at 30 FPS. And this is where Christian and crew got very clever. With the normal structure of game logic, then command buffer calls to the GPU being standard and serial, the quick win is just run them in parallel, with the game and render running in separate threads. Which they did, but added a very clever and most certainly dangerous and ingenious plan. Not only running the logic split, but also on different frames. Now the engine will start the first frame off with standard game logic on the CPU, and then pass this on to render calls on another thread. Meanwhile, the first stage then begins the game logic for frame 2 while this is happening. Once this is done, it passes on to the second stage, as this has now generated the command buffer work which has been passed onto the GPU so that it can get to work on rendering the frame. Now the first stage is on frame 3's logic, the second on 2, and the GPU rendering the very first frame. No syncing is needed as the GPU is not involved in rendering any game logic like physics or light calculation, raycast, etc. Well, in the Last of Us Remastered anyway. And all this is done on the CPU, so each stage can be processed, closed and passed on. But to have multiple frames in process, this will give you big memory issues, as you will need big buffers, rotate them and ultimately clear them when done. But only when done, as this, although very efficient, is also very dangerous and could easily turn into system crash and the dreaded memory stomp, so this needs some care. They achieve this by creating a frame params, a handler that is passed with a unique instance of each frame that lives with it and its data. It's all encompassed here and allows a free uncontended resource that can be used, processed and ultimately destroyed when done. It contains all relevant data for pointers in memory and the mesh data that will appear in the frame, making debugging simple within its design. 16 of these can be viewed in a trace, with the last 15 being tracked, but only 3 live in memory at once, as memory would not allow for 16 frames to exist at once, and the params are rotated through as the game engine runs. This is, as always, had the safe option being taken, which inflated the allocation with over 200 megabytes wasted on this. So to resolve this, they use what they call tagged heaps, simple 2 meg blocks of system RAM from the onion or garlic memory block, CPU, GPU, for the frame section in flight. This is then tagged with a 64-bit integer to reference what is being used. When the frame section completes, the request is sent to release that block or blocks of RAM that have the relevant tag associated with them. If the job needs more than the 2 meg, then another is requested and added with the tag. In these cases, a lock is required, but only small and at each 2 meg block. This is in very rare occasions though, with 99.9% of allocations fitting into the 1 block allocation, meaning at worst you only waste just under 2 meg maximum in a case of memory leak or spike, giving back the 200 megabytes lost with the first process. Not only this, but as the locks are not needed, then contention is non-existent, with pointer addresses being stored in local storage of the executing core, so the entire job runs completely uninterrupted. From reading and seeing what Kristen and Naughty Dog have done here and the work they have put in to get the engine moved over to PS4, but also again making huge strides with the help of the ICE team, SN Systems and other Sony departments, the big strides they made so late in the schedule, albeit exasperated by the migration from PS3, shows how close the game, and this is not as uncommon as you would think, is to finish before it ships. Other games are also using fibers, with a new Mortal Kombat game having these, so I'm confident it will be a large move by many studios to at least try to use them. To be clear, this is not a Naughty Dog invented process, just that they seem to be the most involved and embraced team that has used them so exhaustively within the entire engine, and I think the clear benefits have been shown, with far better CPU core utilisation evident. With the examples given and the now delayed into 2016 release of the first actual game made from scratch in this new engine, the target for 60 FPS is certainly more than still the aim. With the engine being designed now for 60 and the improvements that are being made still to their own engine, along with the SDK and hardware itself, many things can and will still change. If Sony manages to allocate back the 7th core in time for launch, and the example given by Naughty Dog here, with the 25 milliseconds per frame needed, meaning that the GPU is most likely not going to be the issue at hitting this target, with the demo shown last year reported by Edge as running at around 40 FPS, along with the tessellation work on C-line objects and characters as per my demo dissection at the time. This means the frame time is around the 25 millisecond mark. A further core allocation that could handle another around 20 milliseconds of work would be enough to push this into the 60 FPS target, all on its own, so long as they are still CPU bound in the engine. No matter if they achieve the 60 goal throughout, and I can certainly see that happening with possibly a 30 target for the real-time cinematics if they really want to push the fidelity higher than the reveal shown, which would not be a bad result. All not, Uncharted 4 will be a stunning, exhilarating and impressive game from Naughty Dog, and show the potential of the team and engine on PS4. With such hard work and dedication, the wait will be worth it for the bookend of Nathan Drake that started 8 years ago on the PS3 and will now conclude on the PS4. I hope you guys and girls enjoyed this. As always, if you did this or any of my other content, then please hit the like and subscribe button. I really appreciate each and every one of you that does. Leave your thoughts and feedback below, and I'll leave with a few more minutes of footage to see you out. You guys and girls take care, and I'll see you very soon on the next one.
Damn it! Where the hell did he go?
I nearly shot your head off.
Sam, you're okay.
Yeah, nothing I can't walk away from. It's good to see you're alive, little brother. Come on. We got a treasure to find.